Particle accelerators involve using an electric field to accelerate a particle. We're going to be looking at electron guns, so using negative particles, but we can also look at positive particles too. We need to be comfortable with either charge. What we're going to be focusing on at the moment is after we've accelerated the particle, we have some sort of fast-moving particle, we're going to be firing it into a magnetic field. And a magnetic field, if it's perpendicular to the direction of motion of our particle, is going to exert a force upon that particle. It doesn't have to be perpendicular, there are other angles that you can look at, but for VCE Physics we're just going to be looking at if the velocity and the magnetic field are perpendicular or parallel. Perpendicular is when there is going to be a force, parallel is when there is no force. So we've got a particle here, positive particle, and its velocity is to the right. These crosses are representing a magnetic field, and that magnetic field, according to our convention, is pointing into the page. So let's get our right hand slap or right hand palm rule ready to go. Our fingers of our right hand are going to point into the page. Our velocity is going to be represented by our thumb, and that's going to be pointing to the right. So this particle is going to be experiencing a force upwards at this moment in time. Let's imagine a moment later. If this particle is experiencing a force upwards, a moment later it's going to be like this. Its velocity is now going to be in this direction because its original trajectory has been deflected due to that force. Now let's apply the right hand slap rule again. Fingers into the page. The velocity is now going to be pointing upwards at that sort of angle there diagonally, and that force is now going to be again perpendicular to that velocity, a slightly different direction to before, but still perpendicular to the velocity, because that's our right hand slap rule. So what effectively is happening is this particle is now traveling in a circle. We're only seeing a portion of it here. Remember, the conditions necessary for circular motion are that we have a constant magnitude force. Here it's given by F equals QVB. And it's constant magnitude because the charge Q isn't changing, the velocity isn't changing because we don't have a force in the same direction or in the opposite direction of the velocity to change its size. And the magnetic field, we're assuming we're in a uniform magnetic field, so that means a constant strength magnetic field. The other condition necessary for circular motion in particular, rather than it being just some sort of curve, is that we need F is always perpendicular to V. And that's true here. Due to our right hand slap rule, we can see that F and V are always perpendicular, and they're always mutually perpendicular to B as well. So, this is circular motion, a really, really interesting and wonderful application of it because we're getting some of our knowledge from our first area of study when we did circular motion with some of this wonderful work within charges moving within magnetic fields experiencing a force. We said that this is circular motion, and in circular motion we said that some of the forces could be written as mv squared over r. In this case, the centripetal force, or the force pointing towards the center of the circle, is given just by qvb. Now, you might be familiar with when we use F equals QVB sine theta, but because theta equals 90 degrees here, sine theta is 1. So that's why I've just used the QVB version. So QVB is given by mv squared over r. I'm really conscious of the fact that my r's and v's sometimes look the same, so I'm really trying to write them differently. Let's neaten this up a little bit. I notice that we have v's on both sides, so let's cancel off this v and this v. They're both lowercase v's for velocity. So we've got QB equals now mv on r. Now, there's lots of rearrangements you can use for this. One of the most common ones that I've seen is writing it as r equals, so that as the subject. So that's going to be mv on QB. So this equation here gives the radius r of the path. And when I'm talking about that, I'm talking about the center of this circle, that radius that we're talking about here. So radius of path of charge, and that's got to be in meters. M is going to be the mass of the particle. Again, we want that in kilograms. We have Q is the charge of the particle, so of particle in coulombs. B is the magnetic field strength, and we most often measure that in Tesla. So we've mentioned R, M, we haven't got V. So V equals velocity of particle. and that's in meters per second. This is a beautiful application of putting together our circular motion and our magnetic force on that charged particle. Let's now apply this to some exam questions. We've got the 2018 VCE exam question here. An electric field accelerates a proton between two plates. The proton exits into a region of uniform magnetic field at right angles to its path, directed out of the page as shown. So let's have a little look. So these particle accelerators always have two components. This component I often whimsically call the area that makes particle go quick, and that's because we have an electric field. An electric field, remember the direction of an electric field, or the electric field lines, they point in the direction that a positive charge will be pushed or experience a force. And then this portion, that's the magnetic field, and the magnetic field is going to make this particle curve in a circle. So we've been given some data here. We've got the mass of the proton, the charge, we've got the accelerating voltage, distance between the plates, and strength of the magnetic field. Just take care, we have a kilo here, so that's times 10 to the 3, and we have a centimetre here, so that means we can have 0.20 metres. Everything else looks good. Okay, calculate the strength of the electric field between the plates. So rather than looking at that magnetic field information, we're going to be thinking back to our electric field information. The strength of the electric field was given by E. Remember, that doesn't represent energy in this context. And E is equal to V over D. So the voltage we were told in this question was 10,000 or 10 kilovolts. So we need 10 times 10 to the 3. And the distance between the plates we're told is 20 centimetres, which we've already dealt with the fact that that needs to be in metres. So 0.20. And that gives us 5.0 times 10 to the 4 volts per metre. Just double check the unit in that box. Okay, calculate the speed of the proton as it exits the electric field. Show your working. That electric field, and if you're interested, we see this side is connected to the positive terminal of the battery, so this plate is positive here. This side's connected to the negative terminal of the battery, so this side's negative here. Our electric field's going to be pointing in this direction, and we need it pointing in this direction because this is designed to fire protons, and we need them to experience a force towards the right to make them go faster. So that all works nicely. Now, in this field, the field is going to be doing work on this proton. So we have a proton source here, and our proton is going to start here. What they often will specify in the question, but I've reread it and they haven't specified it here, is we're going to be assuming that that proton starts with zero kinetic energy here. Now, yeah, that is a little bit of an oversimplification, but without having an initial velocity, that's the only thing that we can do here. This field is going to be doing work on the proton as it moves from this plate to the other, because it's moving in the direction of the field. And that work is equal to QV. Now remember, we said work was equal to a change in energy. And in this case, it's a change in kinetic energy, and change in would be KE final minus KE initial. But remember, we said the initial kinetic energy was 0, so work is just going to equal the final kinetic energy. So that means work, which also equals QV, is going to equal a half m lowercase v squared. Because this V is for voltage, please excuse the person mowing their lawn outside my house, and this V here is for velocity. So if you need to really over-exaggerate your capital V here. So we're going to be equating these two. QV for voltage equals half mv here for velocity squared. So let's do that. QV equals half m lowercase v squared. Now we are interested in the speed of the proton, so we're going to solve this for v. So we're going to have multiply both sides by 2 to get rid of that a half. We're going to swap things around to QV. You don't need to show all these lines of working out, but I find, if in doubt, show it. Capital V on M. And now we're going to take the square root. Now, whenever we take square roots in physics, we have to ask ourselves, do we need the positive or the negative? Because we're just interested in finding a speed. The positive is absolutely fine. We just need the magnitude. So now let's substitute. We've got 2 times the charge on a proton is 1.6 times 10 to the negative 19. And we've got that voltage is times 10 to the power of 10 to the 3. Could have written that as 10 to the 4. And the mass of the proton, I've forgotten, let's double check it. Mass of the proton is 1.7 times 10 to the negative 27. Okay, let's pop that in. So that is a pretty big number. Let's put it into scientific mode. So we get, if we do it to 2 sig figs, that seems appropriate, 1.4 times 10 to the 6. Reasonableness, check. That's not larger than 3 by 10 to the 8. That's the speed limit of the universe, the speed of light in a vacuum. That seems fine. Okay, let's have a read of the next one. With a different accelerating voltage. Okay, so V no longer equals that 10 times 10 to the 3. That's dead to us. The proton exits the electric field with this speed, 1.0 times 10 to the 6. Calculate the radius of the path of this proton shown in the magnetic field. Remember, we derived an equation for this before. R was equal to mv on qb. So, we need to put in that mass, 1.7 times 10 to the negative 27. The velocity is what we have been told in the question here. So 1.0 times 10 to the 6. The charge of the proton has not changed, 1.6 times 10 to the negative 19. A little point to note, I recommend just putting in the magnitude of the charge when you're doing these questions. Yeah, it's protons, so it doesn't matter, but when we're doing electrons, negatives, putting that in is going to be an issue, so try not to do that because you'll get a negative radius, which doesn't make sense. And the magnetic field strength has not changed. They've told us in the question that nothing's changed there, so let's look that up. So we were told that was 2.0 times 10 to the negative 2. Okay, let's calculate that. Okay, so I've just put this back into regular mode because I didn't really feel the need to have scientific notation. So 0.53 if we do it to 3 sig figs. Does that seem reasonable? Yeah, half a metre seems reasonable given the context of the question. If I got 53 kilometres or, 53 times 10 to the 3, that would maybe be a bit unreasonable. Brilliant. Let's have a look at now. We've got a 2018 Northern Hemisphere time zone exam question. We've got a uniform electric field again, and it accelerates protons from rest. Now this one's specified from rest. The other one should possibly have mentioned that. And we're told their speed, 5.0 times 10 to the 7. That's really quick. So that's the velocity here, because we just care about the magnitude. We've been given necessary data here. It says the protons then pass into a region of uniform magnetic field that's at right angles to their velocity. Brilliant. They are bent into a circular path. We're now going to explain why the path is circular in shape. So let's answer this as concisely as possible, but really linking it to the physics principles that are there as well. So we were told in the question, the protons are passing into a region of uniform magnetic field that is at right angles to their velocity. So let's put it as V is perpendicular to B. We could be that concise. As V is perpendicular to B, we know F equals QVB, where F is perpendicular to V. And if we want to be really fancy, we can say by right hand slap rule. So we know that F has to be perpendicular to V because V was perpendicular to B. We have a charged particle that has a velocity within a magnetic field. So that is what the force is given by. So really important to note that the force is perpendicular to the velocity. Remember, that was one of the conditions we had for circular motion. The other condition was that it was a constant magnitude force, because if it was changing the size of the force, we would get some sort of spiral or a different kind of motion going on. So let's put as the magnitude of F, or you could write that in words, is constant as Q, V, and B are constant. Now, if it upsets you that that velocity says it's constant even though it's circular motion, V is used to represent speed here, but if it really upsets you, just pop a magnitude sign around the V. So as the magnitude of the force is constant, as Q, V, and B are constant, that's what we multiply together to get the force, we have, therefore, we have constant size force, or constant magnitude force, perpendicular to V, therefore circular motion. That last point maybe is labouring the point a little bit, but I wanted to make it really clear that those are the two conditions necessary for circular motion. Okay, fabulous. Let's continue. We're told the strength of the field is 500 millitesla. That's 500 times 10 to the negative 3 Tesla, or you could write that as 0.500. Calculate the magnitude of the magnetic force on the protons. Okay, we just did F equals QVB as part of our explanation. So we've got the charge on a proton, 1.6 times 10 to the negative 19. The velocity we were told previously, 5.0 times 10 to the 7. And we need that magnetic field strength, 500 times 10 to the negative 3. This gives me 4.0 times 10 to the negative 12 newtons. Very small force, but it's just acting on a teeny tiny proton, so that's fine. Okay, another VC exam question. We've got a 2019 one here. We've got a particle of mass m and charge q is travelling at a velocity v that enters a uniform magnetic field B shown in the figure. So these x's are saying that that field is into the page. We've got v is travelling to the right. And it says, is the charge q positive or negative? Give a reason for your answer. So it's travelling in a straight line here because we have no force impacting its motion. But once it enters the magnetic field at this point here, we start seeing it be deflected. Now, to be deflected in that direction, it must have experienced a force this way. If the force was instead upwards, it would have been travelling like this. So let's use our right-hand slap rule here. Align your fingers of your right hand to point into the page. The velocity needs to be pointing to the right. Now, the right-hand slap rule, if you're doing it as I'm doing, I can see that it's telling me the force should be upwards according to the right-hand slap rule. But that's assuming that we have a positive charge. Because we have the force in the opposite direction, that tells us that we must have a negative charge. So, it says, is the charge Q positive or negative? Give a reason for your answer. Now, you'll notice this is only worth 1 mark. It's not enough to say negative. You actually wouldn't get a mark there because you've really just made a 50-50 choice, positive or negative. You need to provide some semblance of an explanation. Now, because it's only 1 mark, it's enough to just say right-hand slap rule or right-hand palm rule, whatever you prefer to call it. You don't need to get into a full proper explanation of the right-hand slap rule because we don't have enough marks to justify writing out that much. So that would be 1 mark. We have the negative paired with a reason for your answer. Just negative does not attract the mark. Now, next one. It says explain why the path of a particle is the arc of a circle while the particle is in the magnetic field. I'd like you to pause and have a go at doing this question here. It's pretty similar to the one we did before. After you've paused, I'm going to write down the answer. Okay, hopefully you've paused. Here's the answer. As this one's 2 marks, I've tried to be super concise. It says, as we've got V is perpendicular to B and F equals QVB, therefore F needs to be perpendicular to V due to the right-hand slap rule. Next point, the magnitude of F is constant as Q, the speed, and B are constant. I don't have a 3rd mark to play with, so I think we're going to leave it there. If you wanted to then, if you had time to say, therefore these are the conditions necessary for circular motion, I actually don't think that's necessary though, because it says in part B, explain why the path of a particle is in an arc of a circle. So we're assuming it is circular motion, we're just saying why is that so? So I think that's perfectly sufficient to write. Okay, here this question differs a little. The reason being we now have electrons. Electrons, you need to be really, really careful because as we just saw in the question that we just did, electrons experience a force in the opposite direction of protons, and that's true in both electric fields and magnetic fields. Now remember, those fields act very differently, but electrons will still do the opposite of what a proton would do in each of those situations. So I would make a big point to myself that these are electrons here. What other information do we have? We're told the 2 plates are 50 centimeters apart, that's a distance. We have the electrons emerge from a second plate and we're told a speed. It's less than the speed of light, that's good. And as they sometimes write these days, and I think they'll be doing that more and more, it says ignore relativistic effects. So we don't need to start looking at any Lorentz transformations or anything like that. So we've been given the mass of the electron and the charge on the electron. So here we've got a different situation. We've got an electron source, we've got 2 plates, and we've got a magnetic field. Just out of interest, this plate in this example would be negative and this would be positive. They could have drawn this with a negative terminal here, a positive terminal here. The reason being, we need the electric field pointing in this direction because the electric field is defined as electric field lines show the direction a positive particle would experience a force. So because the electron's negative, it needs to be in the opposite direction. Just a little note to yourself, how you might see different diagrams in exam style questions. So this section is the make electron go quick. Oh, that looks like a funny face actually. That's the make electron go quick area, and this is the make electron do curve area. First off, we need to calculate the voltage capital V between the plates. Okay, do we have the electric field strength? So we've not been provided with an electric field strength. So my first thought was we could use E equals capital V for voltage on D, because we've got that separation, but because we don't have a voltage, in fact, that's what we're trying to find, and we don't have an electric field strength, that's not going to be the way to go. What we can do instead is the fact that we know the velocity of the electrons outside of the plate. They started with a velocity of 0 here, so we're assuming that they start at this plate here with no velocity at all, and work has been done on them by the field to accelerate them to get to that final speed of 4.2 by 10 to the 7. So what we can do, rather than looking at E equals V on D, we can look at that work approach. Remember we previously said the work done was equal to Q capital V, and that was given by half mv lowercase v for velocity squared. So that's going to be really nice to find out what that voltage is using half mv squared on Q, or if that upsets you, you could write it as mv squared on 2Q. Both of those are mathematically equivalent. So we have the mass of the electron we were told in the question. Remember that was 9.1 times 10 to the negative 31. The velocity we were told is 4.2 times 10 to the 7. Big deal though, we need to square it. Really important that we remember that. We're going to divide that by 2 times the charge. Now I recommend you just put in the magnitude of the charge, 1.6 times 10 to the negative 19. So let's go ahead and calculate. Okay, so we get 5,000 and, let's check my rounding, 16 volts. If you wanted to round this to 2 sig figs, you could write that as 5.0 times 10 to the 3 volts. Okay, the electrons enter a region of uniform magnetic field. We're told the magnetic field strength and that it's at right angles to their path. So that's telling us that B is perpendicular to V. It points in the direction that the electron is going. We want to calculate the magnitude of the force on each electron, and we're going to show our working out. So F equals Q V B. We've got that charge. Just put in the magnitude of the charge because we're just interested in the magnitude of the force. The velocity we were previously told, that was that 4.2 times 10 to the 7. And the magnetic field strength is 5.0 times 10 to the negative 2. Calculating this, we get 3.4 times 10 to the negative 13. Very small force, but it's on a very, very small object, so that's fine. Will the path of the electrons in this uniform magnetic field be a straight line, part of a parabola, or part of a circle? Give your answer. Okay, as we've seen, we have that situation where we have a force is perpendicular to the velocity and it's a constant magnitude force. So the reason they give in the assessor's report is here. So I imagine that it would be 1 mark for confirming it was a circle, and really important to include a reason there, because remember, if you just select one, straight line, parabola or circle, unlikely to actually earn a mark. You need to attempt a physics-related reason. So the reason is because the force is always right angles to the path of the electrons. I would also say because the magnitude of the force is constant, but we only have 2 marks to play with here, so I don't think they required that as part of your answer, but it still would be a good little bit of insurance to ensure that you make sure you mention that. One last thing that I wanted to mention here is they haven't asked it here, but they could have asked you. They could have said which direction would the electron be deflected. So there's different ways that people apply the right-hand slap rule for when we have negative charges. One way is thinking about using right-hand back slap rule. One way is thinking about changing the direction of the thumb. If we have a magnetic field into the page and we have the electron is traveling in this direction, I want you to check with your right-hand rule that you get that the force is going to be acting downwards like this. Double check that, see according to which version of the right-hand palm slap, whatever you like to call it, rule, that you do get that. That's another possibility that they could ask with this, because that's one that's really easily confused because we have that negative charge there. Good luck with doing your own questions.